Well, good morning, everyone. Once again, we are up to section 7.5. We're going to talk about integration strategies. And basically, this is they're all mixed up day, right? So you could have just a simple one that you have memorized. You could have a U substitution, although you could have a chain rule, which is the sort of easy U substitution. You could have one where you want to change the variable, in other words, a real U substitution. You could have an integration by parts. You could have a trig substitution. You could have one that you just want to use algebra or trigonometry on, where you want to change the integrand using algebra. Or maybe you could even have a partial fraction decomposition. And the big goal here is guess the right technique before you run out of time. Okay, that's kind of the way it goes. Essentially, you would just try something. And the more you try, the more experience that you get, the more likely it is that you're going to try the right thing the first time. And so if something is going badly, well, let's put it this way. Since these are actually the first three examples I put on there, I bet they actually work out. So if it's getting really messy, maybe you want to try a different guess. Unfortunately, in real life, it doesn't work that way because in real life, most of them just get really, really messy, and some of them can't even be solved. And so if that's the case, then you just have to do your best. And, given it's a book problem, there's going to be an answer, but in real life, sometimes not so much. Okay, we're going to look at a few of those today. So that's our plan. I don't have any new material for you, except I have some few that I kind of picked. We could do a few of mine. We can do these three. And then if you guys have some from the homework or some that are bothering you, be happy to try a few of yours. Maybe be a little bit of a short day today in terms of new material. But I was thinking, I looked back over the chancellor's note, and they didn't want us to do any official testing until the week of April 5th. And so I'm not going to give you the test until April 5th, but I would like to get started on chapter 11 before that. Otherwise, we're not going to have time to get finished. So maybe today we can talk a little bit about section 7.8 and just get it on the table so that you're thinking about it over the weekend. And then we'll really dive into that first thing on Monday. That's our plan. Okay. Sometime though, I would like you to figure out how you're going to do the little quiz, right? Download it, write on it electronically or with a pencil, figure out how you're going to scan it back in or take pictures of it and get it resubmitted to me. I will grade them as soon as they come in. And what I'm doing is I'm just grading them on my iPad. And so I will write right on your electronic copy, and then you should try to figure out, how to see my comments. Basically, they're either going to be a grade comment, or I think they show up as a grade comment, right? So once it's graded, you can go back in there and look at, the suggestions that I made. Questions about the calendar?
The quiz is still due Monday, right?
Yeah, I think so. I mean, officially, no. Officially, you can turn it in whenever you get it done, because we're kind of in this limbo period where, where we're trying to move forward, but some of our classmates may have higher priorities, right? So if you have a crisis and you just can't get it done, then you'll get it done when you get it done. But I would suggest in an effort to keep moving forward, yeah, I'd probably spend a little time wrap it up this weekend. Katie.
So is it okay since I turned it in early? Am I able to resubmit it for 1 point or no?
For 1 point? I wouldn't worry too much about that. No, let's just, I'm more worried about, the big picture. Like, do I have one from you or not? Okay. And if it's a couple of little things here and there, you know, I think it would be better, you'd be better served just moving forward.
Okay.
Okay, and that goes for the rest of you as well. You know, our goal here is, you know, while we'd like to be masters of this, I'd like you at least to have seen things. And so, you know, we want to try to spend our energy getting as much as we can. So, but I would like you to turn it into me so that I know that you can, you know, download one, figure out how to send it back to me before it gets to be test time. Okay, let's try a couple of these. I'm thinking on number one, it would be really nice if we had a derivative of root x, and then it would be a chain rule. But since it's not there, I really would like to get that root x out of there, okay, because it's causing me grief. And so here's what I would do. I would say, let u be root x, and then hopefully I can make it go away. Okay, now there's a couple of choices here. If you take the derivative, du, you get 1 over 2 root x, right? We have that one memorized. Then you're going to have to substitute for dx, so you're going to have to put this 2 root x on the other side. So you're going to get 2 root x du is dx, but root x is u, so you get 2u du is dx. So some people like to do it that way. Other people would just do this, maybe, square both sides, and take the derivative implicitly. And you get 2u du is dx. So whether you go sort of this way or that way, doesn't make any difference. You're still just going to have to get whatever dx is so that you can substitute. Right? But we've been going sort of this straightforward way. And of course, you could go, you know, you can set x equal to u squared. That might be easier because then the root's gone right at the get-go. Okay, so what do we get? We get the integral e to the u. That looks a heck of a lot easier. And then in for dx, we're going to get a 2u du, meaning we've got 2 times the integral of u e to the u du. And now what? You're saying, well, we changed it. The root's gone. Thank goodness. It's better, maybe. Right? But now we're looking at what?
Integration by parts.
Integration by parts. Okay, because this is a product now. So you got rid of the root, which is good, but now you've turned it into a product. And so now you have to use integration by parts to keep going. And this is kind of the strategy or the way these are going to work out. Generally, you're going to do some work on the integrand, change it to a different form, or use one of the rules to actually change the integral into a different integral. And then that new integral now, you have to solve that one. And sometimes that's going to require, you know, maybe more changing or more techniques. So now this is a hard one because I like u's and v's, right? And so it's a little weird to say let u be u. And so if you knew you were going to get integration by parts, we could have used a different letter up here like w, right? I don't know, maybe I can try this. P is u, dq is e to the u du. Okay, so p dp is du, and anti-differentiating q is e to the u. So what do we get? Don't forget the 2. We've got 2 times pq, u e to the u, minus 2 times the integral of q dp, yeah? E to the u du. And so carrying on, 2u e to the u minus 2. Antiderivative e to the u is e to the u plus c. Got to put the u back. So u was, where am I? U was way up here, root x. So 2 root x, e to the root x, minus 2 e to the root x. Of course, you could factor out the e to the ux, put it in factored form if you want, but this one would be fine. All right, last step. Here's the last step maybe, especially if it's a take home or if you're engineering something. then the last step is share your screen, put this up, and say integrate e to the square root of x with respect to x. And we get 2 times e to the root x, that looks good, minus e to the root x plus c. Okay, perfect. And so we should be in good shape. Questions? If you have to do this, no calculator, no support, no pushing return and getting a little red X that tells you you made a mistake, then, and you've got enough time in your hands, then of course you could take the derivative of this in the forward direction to check your work sort of by hand without a calculator. And notice that you would have a root X times e to the root X. In other words, right here, you'd have a product. So you'd have to use the product rule. And that's not a big surprise because integration by parts is the product rule backwards. Okay, so this one turned out to be a U sub and then an integration by parts. How do we do? Okay. Okay, getting some thumbs up. Well, let's try another one. Here we go. How about number 2?
Looks like a chain rule.
It does. It looks a lot like a chain rule. So if I move it down here and I rewrite it like this, log x to the minus 1/2 power times 1 over x dx, then I think you can see that the 1 over x is the derivative of the log. So it's something to a power times the derivative of something. It's just a straight chain rule, that's it. But it seems like, you know, the 1 over x is a little bit disguised because it's kind of looking maybe like it's a quotient, and it's also kind of looking a little bit like a product. So it would be easy to get confused on this one and maybe try integration by parts on this one. Okay, which, by the way, would probably work. It would just take a heck of a lot longer. So if you like actually physically making a substitution, you can say, let u be log x du 1 over x dx, and of course make this a physical substitution in here. But I usually don't for chain rule. I just recognize it as a chain rule, oops, and then I just go from there. So it's to the minus 1/2, must have been to the positive 1/2 before. I'm gonna need a 2 to get rid of it, and I think we're done. So if you see it as a chain rule, pretty fast, pretty easy. If you don't see it as a chain rule and you try integration by parts, you probably spend 15 minutes, get the same answer. Okay. Now, you guys may be, you know, thanking the virus here because of course you aren't under any time pressure for the next little test. Okay. You know, I mean, if you're going to be fluent with this, part of it is recognize these quickly because you're going to run out of time. You don't have all day, you know, but you guys do have all day as long as you set it aside. Now, that begs the question on the test. What would stop you from just going to Symbol Lab, putting it in, and getting the answer? And the answer is, well, pretty much nothing. Okay, and I would say checking your answer using Symbol Lab would also be a good idea. But what I'm going to want to see is how you supported that answer. So what I would prefer to see in the middle part here is your work. Okay, so I would say it would be not fair to pay the premium and write down Symbol Lab step by step or Wolfram step by step. I want to see your step by step in the middle. Okay, so do the best you can to try to fill that in. But if you're if you want to check your work at the end, you know, using the calculator, that seems like a pretty smart thing to do for an engineer. You know, check your work, make sure it's right before you engineer something and it falls down. Does that sound fair? Okay, so the alternative to that is I rewrite a big section of the test, and instead of just asking you integrals, I ask you questions like, which technique would you use for number 3 and why? Okay, or compare and contrast integration by parts and partial fraction decomposition choose the one that you like the best and give me 3 reasons why you chose it. Okay. And I've been known to write those kind of tests in the past. And that's not to say that the answers to those kind of questions wouldn't be a good thing for you to be thinking about. But we got a lot to do. And I don't want to get stuck here for too long. I want to get on to chapter 11. So I'm just going to give you pretty much a test that has a bunch of integrals. And then I need you to get the answers and provide some justification along the way as to how you got those answers. But, you know, maybe I'll slip a couple of essay type questions in there here and there, but I'm not going to rewrite the whole test and make it all kind of essay based. Okay, it's just going to be integrals, and you're going to do the best you can to solve them. Sound okay? Okay, I don't like number 3. That's why I was blabbing so much. Number 3, I don't know how to do it. Okay, number 3 is really a mess. I don't like the root, right? I don't like the root. That's causing me grief. And I don't like the fraction. That's also causing me grief. So it almost looks like if I could get rid of the root, then maybe the fraction would be some kind of a log. Maybe I could break it down by parts. Maybe I could split the fraction and see if it would work that way. But given a root and the fraction, boy, I really don't know what to do. Any ideas?
Trig sub and then something else.
Yeah, I would think a sub. You know, maybe you would try letting u be the stuff under the root. But then when you did du, you got the quotient rule, and that's going to be a giant, that's going to be really messy, right? If that was a 1 plus x squared and a 1 minus x squared, then I might be more tempted to do like a trig substitution, because you know, like 1 plus x squareds turn into secant squareds maybe if you let x be tangent. And so maybe that would kind of go, but given that there's no squared on the x's, I'm kind of leaning away from trig sub. Okay, so maybe I'll just show you, because this falls into the really nasty kind. This is like, you know, either I let you just grapple with this, which means you might have to grapple with it. You know, maybe some of you will come to you in 5 minutes. This would probably not come to me, you know, maybe a couple more cups of coffee. You know, wandering around not thinking about it is usually when it comes to me. But this is like a terrible test question, because you're either going to see it or you're not going to see it. All right. But here we go. Here's the trick. If we need the integral, let me slide down here, of the square root of 1 minus x over 1 plus x, then what we do is we kind of say, you know what? Normally I would say, you know, what is causing me the most grief? And the root is causing me the most grief. And then I would say, well, what would make this better, right? What would be better? And I'm thinking that if I had squares, it would, you know, like 1 plus x squared, it would be better than just the 1 plus x, because then I'd be leaning toward trig sub. So given that I've tried everything else and I don't know what to try, I would try this. It's the sort of age-old trick of multiplying this by 1 and just figuring out a clever one to multiply it by. Okay, and here's what I'm thinking. I'm thinking if we multiplied it by, what do I want to multiply it by? How about 1 minus x over 1 minus x? That's certainly legal as long as x isn't 1. Which could be a problem, because in the original domain, x could have been 1, right? 1 was okay. So now you got to consider, well, what if I'm concerned about the solution somewhere near 1 and this technique isn't going to work? Okay, let's just do it for all the other values. And so check out what we get. We get the square root of multiplying these together, we get 1 minus x all squared. And then down here in the bottom, we get what? 1 minus x squared. And you're saying, okay, how is that better? Well, it's a little better. I can take the square root of the stuff in the numerator now. and I get 1 minus x in the top, and I get the square root of 1 minus x squared in the bottom. Yeah? And now everybody should be happy. How come?
Can let x equal sine theta.
Yeah, let x equal sine theta, and now the root will go away, won't it? Now you're going to end up with a trigonometric integral that might be really hard to solve too, but the grief was the root, and so now the root is gone, right? So what do we turn it into? We turned it into a problem that looks like a trig sub, and now we're going to do a trig sub to turn it into something that doesn't have a root, and then we're going to have to keep going. But that initial trick of realizing that a 1 minus x squared in the bottom would be a good thing, boy, that's a hard one to see. Right? So if you saw it, awesome. If you didn't see it, well, keep working on problems, right? It's just messy. And you may never see it until you try about 100 other things, right? You might just stumble on it by trying everything there is to try. And sometimes, you know, that's the way it works on these. Okay, so here's what I'm saying. So let's go over here. Let x, right, be sine theta. I'm up here now. I'll rewrite it for you in a second here. Oops, come on, camera. Maybe it'll focus in a minute. Dx, right, is what? Derivative of sine is cosine theta d theta. Eventually, we're going to need theta equals inverse sine of x when we plug it back in. Okay, so here comes the integral now. We got the integral 1 minus x over square root 1 minus, right, x squared. And then we have to put in for the dx, cosine theta d theta. So I'm saying, you know, if you like trig integrals, you're happy. And if you don't like them, well, then you have to, I don't know, get to like them a little better. 1 minus sine squared is cosine squared. Square root is cosine. This cosine cancels with that cosine. I end up with this. And now you should definitely like this integral because that one should be pretty easy. That's memorized, yeah? Hit me with it.
Theta plus cosine theta.
Theta plus cosine theta, right? And then we have a plus c. Don't forget that you got to put the theta back in, and I would like for you to do that, okay? So here you get inverse sine of x, and then you get the cosine of the inverse sine of x. And somewhere back in pre-calc, probably back in trig maybe, we said you should never leave this like this. You need to resolve these. And I would like for you to resolve these because you will never see this written like this. Okay, everywhere this will always be resolved. And so technically that's the right answer, but we want to do a little bit of simplifying. So this is saying I need an angle whose sine is x. Come on, camera. There we go. So I'm going to draw a picture of it over here. Here's an angle whose sine is x. So the sine is the opposite over the hypotenuse. So this side down here would have to be 1 minus x squared square rooted using the Pythagorean theorem. So if I want the cosine of that angle, if I want the cosine of an angle whose sine is x, then I'm going to do the adjacent over the hypotenuse, and I'm going to get the square root of 1 minus x squared. So I'm going to write the final answer as this. Okay, and then there's sort of two reasons why we cleaned it back up. One is it's simpler, right? And two, check out the original problem. The original problem came as a square root of some kind of polynomial. And now your answer's kind of back in that form. Of course, there's an extra inverse sign hanging around, but for the most part, it's back in that square root of 1 minus x squared form. And this is how you'd probably see it, you know, written in the book, back of the book, or on Symbol Lab or something like that. Of course, that would be the final test. See if we can stick it in Symbol Lab, see if we got it, but I'm feeling pretty confident. Let me see if I can share my screen again. Okay, and now we want this fraction. Whoops, not a fraction. We want the square root of a fraction. Will it do it? No, square root of a fraction. And we want 1 minus x up here. And then we want 1 plus x down here. And then I'm thinking, with any luck, oh my goodness, yuck, look at what they did. Oh, that doesn't look anything like what we got.
Do you want to check Wolfram Alpha instead?
You could, that would be the next thing. Check Wolfram Alpha instead. But but maybe what they got is the same as what we've got. It's just in a different form. So the way you would check to see if it's in a different form, the easiest way, take this and graph it. Take our answer and graph it. Are they the same graph, or are they the same graph that differ by a constant, meaning it's just shifted up and down? In which case we got the same answer, just in a different form, right? But maybe it would be easier before we did that, because that looks like it's going to be terrible to type. Go to Wolfram Alpha and integrate. I think that's what we want to say. Integrate the square root of 1 minus, I might need a parenthesis here, 1 minus x over 1 plus x. I think that's it, dx. Okay, go. Oh, that's even worse. Look at that ugliness. Oh, I don't like either one of these answers.
With symbol, wasn't there a way to like they said, try your other answer, see if it's the same?
Yes, there might be some ways to see if they're the same. It would be really super nice here if this were like text and I could just grab it, cut and paste it into Desmos. But look at it, it's you can't do it. And so the only way to see these 3 answers are the same would be to go over here to Desmos, graph them, see if they're the same. And then it's just a matter of algebra to show that this answer is the same as our answer. Okay, but before I tried the algebra on this messy thing, I think what I would do is I would check to make sure I didn't make a mistake by looking at the graphs first. Okay, so you'd go to Desmos, and then you'd type our answer in, which I like. In Desmos, you can do the, to the little -1, but I like typing arc sign because it's faster. Square root 1 minus x squared. Okay, so there's our little piece. Notice that it's only a little tiny piece here because restrictions on the domain, right? X can only be between -1 and 1. Because if it's more than that, look at what happens. You're going to be taking the square root of a negative. This is a suggestion as to why maybe their answer is going to be better, because I think their answer is going to include a bigger domain. Let's see if we can, what did I do with it? Oh no, closed it. Okay, hang on a second. I didn't like the Wolfram Alpha one. It was too hard to type. So I'm going to put this one back in. Square root, fraction, 1 plus x. And then down here, whoops, was it minus on top? It was minus on top.
Yeah, it was.
Okay. 1 minus x, 1 plus x dx. Okay, let's get this in here. Okay, so here it is. It's looking a little bit like ours. I see an arc sign, right? I see sort of a quotient over here. They're not looking too bad. I'm going to tear this off. Oh, if I tear that, wait, stop sharing, start sharing. Here, if I share my whole desktop, you'll be able to see them both. Okay, so I put this over here, and then I try to drag this over here so I could see to type it. And then let's see, whoops, I still can't see to type it. Okay, so here we go. Here's what they got. They got square root of minus x. They're going to do a fraction. So I'm going to put this in the, oops, yeah, I'm going to put this in the bottom. What did they say? Minus x plus 1 over 1 plus x. I'm going to go back up here. Put minus x plus 1. Go fix this. Okay, now that's times 1 plus x. And then it's plus 2 arc sine of 1 over root 2 times the square root of 1 plus x, right? And then we've got plus c. Add a slider for c. Hey, this is looking pretty good. Check it out. If I slide their answer down, just the right amount, I think it's going to land right on top of ours, yeah? So C would be about a negative 1.6. We could get a little closer if we wanted to maybe say minus 2 to 0 or something like that. So we have a little bit more accuracy. We could slide a little tighter. So I'm kind of thinking their answer and our answer are the same here based on this picture. Are we good? So whose answer is better? Our answer is better. It's simpler. Okay, and it's the one we got. But so do this for me. Don't write their answer on your quiz. Because the only way you can get their answer, because no one would get that answer if they did it by hand. Okay, so that just tells me, okay, you can use Symbol Lab. Awesome, you get some points for that. But I can't give you full points if you don't do a little something on your own. So you got to show me how you know that it's the right answer. And you got to kind of convince me of that by showing some work. Does that sound fair? Okay. I didn't like that one. That one was hard. It was messy. You know, it was tricky at first to know what to do to get started. It was hard to confirm using Symbol Lab to make sure that we were right. But maybe that's a pretty good, that I think would be fair as a take-home problem. And there's no chance you would ever see that in class in a timed environment because, you know, some of you would see it right away and some of you would, you know, maybe if I put a different problem on, you would have seen a different problem right away. And so I don't think that one would be real fair in the classroom. Okay, I got a few more. In fact, I sent you a whole page. Here's a whole page of them, right? So this is, I think it's in an announcement. I sent you in the announcement. So if you just can't get enough and you want to just keep doing more, well, yours will be in focus when you download it. You know, here's a whole bunch more for you to try to take a look at, right? And so if you're just sitting around the house and you're bored, you could say, well, here's a few to try. So, you know, like number one, I don't know, it's a rational polynomial, top's bigger than the bottom. How about divide? Divide and natural log, right? Number two, I think maybe if you factor a t out, you'd get a t squared minus 9, which is t minus 3 plus 3. And then I do partial fractions. Right? Number 5, that looks like the same trig sub that we just did. Try 3 sine theta. Okay. Number 4, that looks like one that I sent you in an announcement, right? What do we have when we have multiple angles? Of course, in this case, you could use the half angle formula on both, which is what I would use. Okay. Number 8, save one of those copies of sine. Uh-oh, they're both even. You're going to get stuck using the half angle formula. Okay. So there's a bunch of them for you to try. And I would go through and do a few of these for some practice. And then, ooh, oh, I just saw that one. That one's ugly. Yeah, it's really ugly right now. It's not in focus. What about that? That looks terrible. What are we doing about 18? Come on, camera. I'm going to try a new solution for next week. I'm going to try whiteboard instead of the camera. Up there it goes. What are we doing with that? Any ideas?
Could possibly do a trig sub.
Yeah, okay. What do you want to sub for the trig? I mean, if you let x be cotangent theta, then 1 over the cotangent is the tangent, and the inverse tangent of the cotangent, hey, that's kind of
just
clever. I wouldn't have done that. I like your approach. I need some paper. Hang on.
yeah.
That is a crazy idea. I would have never done that. Let me see, now that you've got me curious, if I can do that. That sounds really good. Okay, and I don't know what's up with the focus there. It's better. Okay, so what about x is cotangent theta? Now, of course, you need to know what the derivative of cotangent is. Do you know the derivative of cotangent?
Negative.
Negative 1 over 1 plus
Neg-
x.
Is it negative cosecant squared?
I think it
I'm
is.
thinking of something else. I was thinking of inverse tangent.
Oh yeah, inverse tangent. No, I was thinking of just the substitution, right? We need the derivative of this cotangent. So I'm thinking minus cosecant squared. I think that, is that Curtis? I think that's right.
Yeah, that's, my brain
Okay.
got confused.
So inverse tangent of 1 over the cotangent. But what is 1 over cotangent?
Tangent.
Tangent times minus cosecant squared theta d theta. Hey, I like this. What is the inverse tangent of the tangent?
Theta.
Theta. So pull the minus out here. Minus theta cosecant squared theta d theta. Well, we changed it from an inverse tangent, right, into a straight up trig problem now. But now it's looking like we'd have to use what?
Integration.
Parts.
Integration by parts. Some of you, here's how I would have started this original. I wouldn't have thought about doing that. That was kind of clever. And now it's obviously parts, and now you have to keep going. If you start up here, I would have done this. Let u be the inverse tangent of the 1 over x, right? Let dv be dx. I would have tried to use parts in the first place. But remember, parts are disguised when one of them is going to be 1, right? That's a kind of a disguised parts. So you could have either tried parts originally, or you could try this and then end up using parts down here at the bottom. I certainly like your approach. I think it was easier than mine. And it's obvious, it's much more obvious that it's parts now than it was before. Should we keep going or call it good? I don't want to keep going. I don't like cosecants, right? But, but we could. And so now you'd have to choose. Do you want u to be theta and dv to be cosecant squared theta? Or do you want it the other way around? And the answer is what?
Well, if you want dv to be cosecant squared theta, then you can just use anti-differentiating that. It's just going to be, what, negative cotangent?
Mm-hmm. So du is d theta, and v is negative cotangent. Is that right?
Yeah.
Yeah, negative cotangent theta. So we get, maybe we should put this minus back in here. We'll put it back in here like this. Put this one back inside.
Yeah.
And then we can maybe avoid losing a minus sign somewhere. So I'm gonna put this one back inside like that.
Yeah.
And then I'm gonna make this plus, okay?
And at that point, you just finish the parts.
Yep, just finish the parts. Okay, whoops. I get UV theta cotangent theta minus the integral V du cotangent theta d theta. So it's getting better. Do you know any functions whose derivative is cotangent? Uh-oh, halfway memorized.
You.
Do you know any functions whose derivative is tangent?
Oh, it's that like natural log of cosine, isn't it?
That's the
Yeah, it
natural
is.
log. That'd be the natural log of the cosine, right?
Yeah.
Now we've got the cotangent. So I'm kind of thinking it might be the natural log of the sine.
Yeah. That's what I'm
Then I'm
thinking.
thinking we'll need another minus sign maybe. So this would be my guess. But it's a guess. I mean, you definitely have to check these signs and these functions, but I'm thinking this is pretty close. Of course, we'd have to put the theta back in, right? Where's our theta? Theta's back way up here at the top. Theta is the inverse cotangent of x. So you'd have to put that back in at the very bottom, and then we'd see if we're right. Ooh, I like this. This is a challenging one.
Yeah.
So you could check this sort of a piece at a time. Like you could, here, I'll share my screen again. You could just check this one piece at a time. You could just check the second integral if we wanted, which was, I'm going to use x. I'm going to use minus x, minus, what was it? Minus x cosecant of x squared. Not squared there. Squared. I think that's it, isn't it? Dx. So we'll see if our second answer is right. How about x cotangent minus the log of the sine? Uh-oh, lost the minus sign. But that shouldn't be too hard to get, right? We should be able to fix that up. So it's believable that I could get this minus sign wrong. And I think that makes sense because think about the tangent again, the integral of tangent. Isn't it the opposite of the log of the cosine? So this would have to be the positive one. So this is the positive one, and there's the minus sign right there. Now we're not done. We still have to put theta back in, and I'm hesitating. I'm going to tell you this right now, and then I'm not going to write it on all of your tests. I already wrote it on Katie's because she turned hers in early. Some of you didn't resolve the angles. So if you haven't turned in your test yet, make sure you do this next part because it takes me like 25 minutes to write it all out on your test. And rather than write it on everybody's test, why don't you just fix your test before you turn it in? Here's what I need. I got theta cotangent. X was way back up here. Theta was inverse cotangent x of the inverse cotangent minus the log of the sine of the inverse cotangent. That's a cotangent. Cotangent of x, right, plus c. Okay, so what are we doing now? We're just doing trigonometry. That's it. There's no calculus going on, but trigonometry is certainly part of calculus. How about the cotangent of the inverse cotangent? What's that? Whoops, forgot one. We're supposed to substitute for this one too. That's an inverse cotangent of x, right? times the cotangent of the inverse cotangent. So what's the
Just-
cotangent of the inverse cotangent? X. So we get X inverse cotangent of X. So that's there. This, I put it in the front. And then it begs the question, what is the sine of the inverse cotangent? And for me, I always draw the triangle for this. So this says I need an angle whose cotangent is X. So put the triangle over here. Cotangent is the adjacent over the opposite, yeah? Because it's 1 over the
Yeah.
tangent. So this is X and this is 1. And that makes this side the square root of X squared plus 1. So if I need the sine of this angle, then the sine is 1 over the square root of X plus 1. So I get log of 1 over the square root. I'm going to write it this way, 1 plus X squared plus C. But I can do more. If you don't like fractions, then we can do more, because isn't this just to the -1 power? Wouldn't that flip it over?
Yeah.
And when we have the log of something to a power, the power can come down in front.
Yeah.
Okay, so I'll write it in 2 steps. This is square root 1 plus X squared to the -1 power. This power comes down in front, making that a positive. And now we got the log of the square root of 1 plus X squared plus C. I would say that is about as simplified as we can get it. It looks pretty simple. The step I need you to do, especially on the quiz that you haven't turned into me yet, is this step right here where we resolve this using this triangle. Okay, so make sure you guys at least clean that up for me, and then we should be good. And now I'm worried about checking, but I'm going to check anyway because now we're being kind of thorough. So here comes the screen again. Share. And now we didn't want to check our halfway result. We want to check the whole thing. So the whole thing was inverse tangent arctan of 1 over x dx. And we say x arctan 1 over x. Oops, close. 1/2 the log. Oh, look at how close this is to ours. See this root right here? This root is to the 1/2 power. So the 1/2 power can come down in front. So we get 1/2 the log of 1 plus x squared. There's the second part of their answer. And then check this out. This inverse cotangent is the same as the inverse tangent of the reciprocal. So that's a trig identity. So this is, right, is a trig identity that says that the tangent of the inverse tangent of the reciprocal is the cotangent. And so if you don't believe that, put it in Desmos. And there's their answer. Whew. Oh, you can't see it. Sorry about that. I was on the other screen. Okay. So how do we know these two things are the same? Trig identity. You either remember it, which you probably don't because no one memorized arctan trig identities. So put that on Desmos to check. Right? So maybe I'll do that for you as well. Got to get to the right window. Share this, go, Desmos. Where's my thing here? Desmos, okay. So now we want to check that those two are the same. So we're going to put them in here. We're going to say inverse cotangent, arc cotangent, right? That looks like that. And then we're going to say arctangent 1 over x. And that one's going to look like that. And you say, well, wait a minute, those aren't the same. So what's the deal? The deal is, look at them though. They have the same slope everywhere, don't they? In fact, these two are exactly the same on this side. But on this side, they're shifted by a constant. But they have the same shape. And so there's definitely something going on here. They're like the same, but not really the same. If you had to anti-differentiate across zero, we would definitely have a problem. There's something going on here at zero. There's a big jump. But other than that, these two functions, okay, have the same shape. So they have the same derivative. And I think we're worried about big picture right now. But certainly if we were concerned about x equals 0, we would have to say there's something going on, right? Because the second problem has a jump, whereas the first problem is nice and continuous. So which answer is better? Oh boy, that's a tough question. I think ours is better.
Yeah.
Okay. I guess what I'm arguing is that you can put these in different forms that differ by a constant. And just because you looked it up in Symbolab doesn't mean Symbolab's going to tell you what you got. You might have to do a little work on it to make sure they look the same. Okay. That's all I have for these. The rest is just going to be, it's a little game for you to play when you're bored. I gave you 25 of them, right? So this is like a challenge. So if you do Sudoku, you can do this instead, right? Because this is more challenging than Sudoku. And it'll take up a little time while you're quarantined in your house. Any questions?
No.
Okay, I want to get one more thing on the table. I'm going to keep you just a little bit longer. I want to get one more thing on the table before we move on. And it'll get us warmed up for next week. So here it is. I'm going to get a little bit more organized here. Okay, so here it is. Here's what I want to consider next. I want to look at some of these interesting places, like the places where we have asymptotes or holes or jumps. In particular, I'm interested in this question. What is the area under 1 over x squared? I'll put it over here, 1 over x squared. Okay, so here's our problem. We want to know the area under 1 over x squared. Essentially, we're going to look at this picture right here. So share my screen again. Wish there was an easy way to do this, but whatever, this works. We've got a function, f of x equals 1 over x squared. And we want to know, hey, what's the area underneath here? And right away, I think you can see a problem. What's the problem?
Infinite.
Infinite, not bounded, right? It goes all the way up, 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 all the way to infinity. And not only that, but if I go over here, even though this gap is getting really small, there's still a gap, right? This is an asymptote. So it's not bounded. And so this is our new problem. Our new problem is, how do I find the area of an unbounded region? Well, of course, to find the area, you do something like this. How about the integral from, I'll just go from 1 to 2 to start us out, of 1 over x squared dx. Whoops, get over there, dx. And you'd say, well, from 1 to 2, right in here, if we're just focused on this little section right in here from 1 to 2, right, then that area looks like it's about a half. Are we good? This should be pretty easy, right? You could you get this half on your own, like without Desmos estimating it for you? And the answer is sure, I think so. You'd use the fundamental theorem of calculus, right? And you'd get what? Am I on the screen? Yeah. Come on, all this anti-differentiating hard ones, you can't forget the easy ones. How do I do 1 over x squared?
It's just the power rule.
It's just the power rule. So x must have been to the -1 power. I need a minus to take care of it.
Yep.
And then from 1 to 2. So I get plugging in 2 minus 1/2 minus plugging in 1 minus 1 minus 1/2 plus 1, oops, equals 1/2. Yeah, are we doing good? Here's the new problem. What if I go from 0? Ew, undefined doesn't look so good. In other words, if I go from 2 right here back this way, this fact that this is unbounded means this goes all the way up to infinity. So we end up with infinitely large. Okay, that's not to be too unexpected. That seems kind of reasonable. It's unbounded. It goes on to infinity. Okay, no big deal. What if I start at 1? Okay, ready? This is going to be so cool. This is going to be so cool. What if I start at 1 and I just keep going? Ready? Since I typed a Y, it's going to happen. What? How come it doesn't know how to find this? Look what it says. It says, I don't know how to find this. If I go to a big number, it knows how to find it. What if I go to 10,000? It's looking like it's about what?
1.
1. What if I just keep going bigger and bigger? Eventually, Desmos runs out of decimal places and doesn't know what to do. But right before it runs out, it suggests that if I keep making the upper limit bigger and bigger and bigger, then the area is getting closer and closer and closer to 1. And we would say the area is 1. Pretty cool, huh? This is how it works sort of on paper. So if you're on paper, you'd say, well, I want to know, right? Here's my 1 over x squared. It's going down like this. I'm starting at 1. I'm finding this area. So from 1, basically, to right, something really big.
Would
You
we
would
ever
write
do-
from 1 to infinity of 1 over x squared dx. Now, of course, we already know that you shouldn't use infinity as a noun. It's not a to infinity. It means I'm going on and on and on to infinity. So a different way to write these, by the way, this has a name. It's called a improper integral. Because one of the limits of integration is going to be infinity. Here's how we rewrite it. We say, take the limit as t goes to infinity of 1 to t of 1 over x squared dx. In other words, we can't do it when the upper limit is infinity, but we can do it when the upper limit is a number, and then we let that number get bigger and bigger and bigger and bigger. Okay, so how would we do this problem? You just do this integral like we did before, and then finish it up with the limit problem, right? From way, 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 way back, like about 25 years ago when you were in Calc 1, remember that? Seems like a lifetime ago now. So we already solved this integral. It was minus 1 over x, right, from 1 to t. So plugging in, I get the limit as t goes to infinity of minus 1 over t. And then I plug in the 1, so I get minus a minus 1. So I get plus 1. Oops, sorry, moving up. And now I want to find the limit as t goes to infinity. Well, what does it go? What does this go to?
It approaches 0.
This goes to 0. So the overall limit would go to 1. For improper integrals, if the limit doesn't exist, then we say the area doesn't exist. If the limit does exist, then we say the area is equal to the limit. So we would call the area under this curve 1 is what we would call it. And it's a really weird idea because of course this isn't bounded, right? It's open. How can it be open and yet have a finite area, right? It's a weird idea. Okay, and of course we are cutting it off here, right? We're cutting it off at x equals 1. Yeah, we're cut off right there. So from here all the way out here, even though this stays open, it still has a finite area in here. Pretty neat, huh? Now, not everything works that way. Check this out. What if we had just gone x squared, right? From 1 over. Well, this is definitely infinite, right? This is going to be infinite. So that's not gonna work. By the way, we could put an f of x in here if we want the general case. Okay, and you can see that that's getting really big. You know, 3 times 10 to the 20th. Okay, that's really big. But now that we found, so if the function is going up, then what do you think that the area is going to do out here?
Also going to go up.
Also going to go up. Okay, so anything that goes up, right? This is going to go up even faster, right? This is going to go up even faster. Giant area. This is going to go up slower, right? But still has infinite area. So if we want to have any hope of this thing getting an area, we're going to have to at least make the function go down, yes? So if we started with something like this, 4 minus x, then for sure, I'll go to something smaller, 1 minus x. For sure it goes down. Oops, that doesn't work. 2 minus x there. This goes down, but it actually closes off. So it's actually bounded. So when it's bounded, we know how to find the area. That was like old stuff way back from sort of the end of Calc 1 and the beginning of our class. But what happens when it goes down, but it's not bounded? Do you know any functions that do that other than 1 over x squared? Yes. Why don't we try this one? 1 over x cubed. Looks to me like when x gets bigger and bigger and bigger, that even though this, right, even though this is open, it looks like we're still going to get a finite area. In fact, if we put in 10 million, Desmos thinks it's going to be right on a half. So I'm saying that if we put in something a little smaller than that, it would be getting closer and closer and closer to a half. So it looks to me like you'd still have an area in there. You know anything else that goes down?
1 over x to the 4th.
X to the 4th, x to the 5th. Okay, yep, you could explore those. What else? How about this one? I like this one. How about e to the minus x? That one goes down, doesn't it? And so what about that one? Does that look like it has an area? It kind of looks like one to me. Is it sort of stabilizing? Look, as I add zeros, right, it seems to be pretty stable. So it doesn't look like the area is going to be a nice, integer value, but it certainly looks like it has one. Okay, ready? Here comes the messy one. Ready? Check this one out. 1 over x also goes down, doesn't it? Open, asymptotic. Uh-oh, but watch this. As I add zeros in here, look at what's happening. Uh-oh. What do you think? I'm thinking that there's no area. So what's happening is that 1 over x is coming down, and it's closing this gap, but it's not closing this gap fast enough. Meaning that you're still adding enough area that this keeps getting bigger and bigger and bigger and bigger. So it's going to be a race. It's going to be a race as to how fast it's closing this hole, right? It doesn't close the hole all the way, but it is certainly closing it. Let me see something else that goes down. Here's something else that goes down. How about log x? It goes down, but it goes down even slower. Do you see that? It goes down even more slowly than x. And so if 1 over x doesn't close the gap, then I'm thinking 1 over log x isn't going to close the gap either. So how about this? What about x times log x? Check it out. It's closing the gap faster, but according to our estimate here, doesn't look like it's close. Well, does it? Maybe I just have too many zeros. Doesn't look like it's closing it fast enough. Yeah? Is this making sense? But check out this function. This function is going down just a wee bit faster than x log x. And this one's going down fast enough, right? This one's going down fast enough that it actually closes it off. It actually get a finite value of the area. So this is going to be our next topic. We're going to be trying to find improper integrals. We're going to be trying to find integrals on regions that aren't bounded. And it's going to be pretty interesting because some of them, if it goes to a number, we say they converge. And so some of them are going to converge and some of them are not going to converge. Some of them are going to run off to infinity. And we would like to explore them and try to figure out which ones do which. And that's section 7.8. Okay, so in 7.8, we're going to explore a whole bunch of integrals that look something like this. The integral of blah, 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 which you're supposed to be good at now. I should be able to put a whole bunch of different functions, f in here, and you ought to be able to handle them, right? Like the 25 I gave you on the practice sheet. And now we're interested in asking, if I start somewhere fixed like A, and I keep going and going and going, like maybe to infinity, which means you can't really go to infinity, just keep going and going, then what happens with this integral? Do I get a finite value? Or does it diverge and run off to infinity? Or maybe negative infinity? Okay, and that's what we want to talk about on Monday. So if you have absolutely nothing else to do, then knock out 30 integrals, those 25 integrals, do all your homework, do the quiz, read section 7.8, and oh, hey, and if you're really bored, you could certainly read section 6 and 7 in the book too. Section 6 says, if you don't know how to do the integral, use symbol lab. Yes, that's kind of what actually it says, if you don't know how to do the integral, look it up in a table of integrals, which actually nobody does anymore. And then the other section says use symbol lab. Okay, so I thought we could skip those because we've been doing those techniques all along. But then if you get all that done, then you can kind of preview next week by looking at section 7.8. And if something happens and you can't visit with us on Monday, then when you do get free and you do get some more time to work, then you take a look at 7.8 on your own and you won't get behind. That's what we're going to be doing on Monday. Okay, that's all I got for you. Any questions before we go for the weekend?
I had a question about the homework.
Okay, fire it up.
I have this one problem that I can't seem to solve. Let me see. I can. It's this one right here.
Okay, let me make it bigger so I can see it. Oops, I want yours to go bigger. Oh, there it goes. Ew. All right. Integral 0 to 4. I'm thinking x squared plus x plus 1 over x
Is
plus
that from
1 squared.
7.5?
This is 7 for homework.
Oh, okay.
Yeah, that's helpful, isn't it? That's going to be sort of an important question because it's going to tell us if it's in 7.4, we're probably using partial fractions. And if it's
Yeah.
in 7.5, it could be all mixed up. We don't know. But either way, I would be looking at this thinking partial fractions.
Yeah, that's what I tried.
Okay, so I would try integral, right? You're going to plug in the 0 to 4 at the end. You're going to get something over the x plus 1 square, the x plus 1.
Mm-hmm.
You're going to need something over the x plus 1 squared. And then you're going to need something over the x plus 2. And if you can find this a, b, and c, right, then I'm thinking that we could do each one of these. This one would be a log. This one would
Okay.
be a log.
Mm-hmm.
And this one would be a power rule.
Right.
Okay. So is the trouble, so that was the setup. Is that what you tried?
Yeah, the setup isn't what's confusing me. It's when we get to here. Let me show you if I
Okay.
can what I did. So I tried. I have.
Uh-oh, I lost you. There you are.
So I did that. I split them up into the 3 fractions like you did.
Okay.
Because this,
I think,
this one,
yep.
because this one is a quadratic, I was thinking I had to put a linear expression in the numerator.
Not when you have repeated linear factors. If you have irreducible quadratic factors, then yes. But if you have repeated linear ones, on this one, all you need is an A on the top.
Okay.
Okay.
Okay, that makes
Did you
things a
come
lot
down here
simpler.
and you get something you couldn't solve? So you couldn't find an A, B, and C, D that made this work, right? Like there
Yes,
weren't any.
because once I get, yeah.
Yeah, because it's look at that, the reduced row echelon form down below. God, this is beautiful. Are you doing that on your iPad?
Yep.
Man, you're going to be, yeah, just have to deal with my poor writing on the iPad when you see my corrections. like a
Yeah.
kindergartner. Yours is beautiful. Yeah, look, you got,
Thank you.
you got D is 3, but then in here, you can't figure out which ones C and B are, right? There are multiple choices.
Yeah.
So I think what you need
this is where I
here
got stuck.
just an A on the top. That's what you need.
Okay. Okay.
And then try it again. I think it'll work.
Okay, that helps a lot.
Yeah, I think that you, I think that in Symbolab, you may be able to say decompose, right? You might be able to just tell it to decompose it for you, and that might be a way to check your work too. And
Okay, I'll make another one.
Okay, other questions?
There was one on the 7-3 homework that I did, but it said my answer was wrong, and then the answer I got in Symbolab was right, but I have no idea what was going on there.
Could have been a couple things. WebAssign does its very best to recognize multiple forms of the answer. So it's possible that you just had it in a form it didn't recognize, even though it was equivalent. If you made a picture of the graph and the graphs look the same, then I would say your answer is fine. If you want to fight it, then it's an algebra problem. You just have to dig in there and fight it and show that they're the same. And I'd be happy to kind of go through that with you. But it's not the most important thing in this section, right? Showing your answers are equivalent. But if you want to do that, send me the problem and I'll work it out and send it back to you.
Yeah. Okay.
Okay. Okay, anything else? Anything from you guys that are just listening in? I see Kevin, but I don't hear you. Yes, no, I'm getting a shaking head. Okay, no, you're feeling okay. All right, well, I will be in and out over the weekend. So if you send me an email, I will get back to you. Maybe not quite as quickly as I do during office hours or whatever, but I will get back to you over the weekend. If you get stuck on your quiz, send me a note so I can get you unstuck. And that way you can, try to get that figured out sometime over the weekend. The rest of it, otherwise, I think have a great weekend, and we will see you guys back here on Monday.
Sure.
Alrighty.
All right. Have a good
Bye.
weekend.
Yep.